So having described the algorithms for implementing the reliable broadcast services that we defined, let's talk about their performance. And it is important to compare these algorithms in terms of their performance in order to be able to understand different costs or different performance trade-offs involved in supporting different levels of reliability. Okay, so to be able to discuss performance, we first need to introduce performance metrics. So performance metrics for distributed algorithms are different from those used for sequential algorithms simply because we don't have just a single process here, right? So we have multiple processes executing concurrently and exchanging messages. So we need different sets of performance metrics in order to be able to evaluate these algorithms. So what are these metrics? So the first metric is called communication complexity, and this is simply about counting the number of messages. So in the specific context of broadcast algorithms, we will be just looking at a single message broadcast, and then we will count all messages that are being generated, exchanged, and so forth as a result of a single broadcast invocation. Okay, so this is communication complexity. The second metric is called time complexity, and this is also referred to as latency. Then the term latency, of course, comes from communication networks, and this is very appropriate in the case of distributed algorithms because they are essentially operate over a communication network. The time complexity is measured in terms of message delays, and a single message delay occurs between the event of transmitting a message over the point-to-point link and until this message is delivered by point-to-point link at the destination. For the sake of calculating time complexity, we will be assuming that local computation takes 0 time. And this is a natural assumption to make in a distributed system because the local computation time is thwarted by the message delay. So message delay is the major factor in the latency of algorithms. So having local computation, having this assumption of local computation taking time 0 has an interesting consequence for the broadcast algorithms. So when we are performing the basic step of iterating over a set of processes and sending a message to every such process through a point-to-point link, all these steps are actually taking place simultaneously at the same time unit, right? This is just because the loop, a single iteration of the loop takes time 0. And since all these messages are broadcast at the same time, then the number of message delays to transmit all these messages to their destinations is going to be just 1. And this is because all these message transmissions overlap, and therefore they just all occur within the time it takes for a single message to arrive to its destination. Okay. So this is time complexity, and finally, when we will discuss performance, that we in most cases will be just focusing on best case scenarios. So best case scenarios are the scenarios in which we don't have any failures, so failure-free scenarios. And this is often what people are most interested in practice, because failures are relatively rare, right? So we can't ignore failures, but they don't occur so often that they have a major impact on performance. So in practice, we mostly be interested what happens in the cases when there are no failures. Okay, so when the system is expected to operate to its best. And so for that reason, most of time we will be evaluating these two metrics, communication complexity and time complexity, in the scenarios where we don't have any failures. Okay. So having introduced the performance metrics, let's see what they are for the algorithms that we have discussed. So first, for the best effort broadcast algorithm, which is called basic broadcast, the communication complexity is simply n, or order n, right? Big O n. And this is because what we do in the basic broadcast algorithm, we just iterate over the destinations, and to each destination we send one message, right? And obviously this is the best we can hope for in any broadcast algorithm, because we have n destinations, so we need to ensure that message reaches all these n destinations, so that can be accomplished with less than n messages. So in this sense, the basic broadcast algorithm has the optimal communication complexity. So what happens in terms of time complexity? So it just takes one message delay for the reason that we discussed. So for measuring time complexity, we disregard the time of the local computation, and therefore all messages are broadcast at the same time, and therefore it just takes one communication step or one message delay to deliver all these messages. So this is just one message delay. Okay, so what happens with the eager reliable broadcast algorithm that implements reliable broadcast? So here communication complexity is higher, and this is because just as in the BEB implementation, we have this initial dissemination of message. The story does not end there. So every process that receives a message from the BEB layer will also need to rebroadcast it or echo it to all other processes. Okay, and we have n processes in the system, and every process echoes the message to all other n processes. So n times n is n squared, and therefore the communication complexity of eager reliable broadcast is n squared. So as regards time complexity, as you remember, we deliver a message immediately as we at the moment that we receive it. We don't delay message beyond that, and therefore the time complexity is exactly the same as the time complexity for the basic broadcast algorithm. So finally, what happens with uniform reliable broadcast implementation, the majority ARC algorithm that we discussed? So the communication complexity of majority ARC in the best case, and recall that we're just looking on the failure-free scenarios as we discussed. So what happens there? So the communication complexity is essentially the same as the communication complexity of eager reliable broadcast. Why? So remember that the main difference between these two algorithms is that in eager reliable broadcast we first deliver a message and then we echo it. In this algorithm we first equal message and then we deliver it. So we just switch the order, and therefore communication complexity is not affected. It's just exactly the same, right? So this is n squared. But time complexity is actually higher. Why? Because of this delay of a message when it is received. So when message is received by majority ACK algorithm from the underlying best effort broadcast layer, it is not delivered immediately. It is put into the buffer called pending, and it sits in this buffer until it accumulates a majority of acknowledgements, right? And that takes another communication delay, another message delay. Okay, so the time complexity for a majority ACK algorithm will be 2. If one message delay to just propagate the message initially, and another message delay to wait for the acknowledgements. Okay, so we can already notice interesting things that going on here, right? So we can see that as we progress through the different levels of reliability, from lower to higher reliability, the communication cost grows. So as we progress from a basic broadcast algorithm to eager reliable broadcast, which supports a higher level of reliability, we go from communication complexity which is linear to communication complexity which is quadratic, right? So supporting stronger reliability comes at the price of message overhead. Okay, so anything stronger than the guarantees of best effort broadcast, so either reliable broadcast or uniform reliable broadcast, requires higher message overhead. Okay, so this goes between linear to quadratic. Now, if you look at the time complexity, then again, these two algorithms differ in these terms, right? So again, we're supporting stronger degree of reliability, we also grow the time complexity. So it takes one message delay for to deliver a message for both basic broadcast and eager reliable broadcast. But then when we're progressing to the majority ACK algorithm that supports stronger reliability guarantees of uniform reliable broadcast, we have to pay in an extra message delay. So what we can see is that basically the conclusion from this picture is that supporting stronger reliability comes at a price, and this price manifests itself in terms of both message complexity, quadratic versus linear, and number of message delays, and time complexity, one message delay versus two message delays.